All right, so here's another problem involving a Desmos or the quadratic regression function on the graphing calculator to find the equation. It says a fan threw a souvenir football into the air from the top of the bleachers toward the bottom of the bleachers. The table shows the height of the football in feet above the ground at various times in seconds. And so you have your table here. If the football was not touched by anyone on its way to the ground, about how long did it take the football to reach the ground after it was thrown? This is where you would need an equation because you would have to set your equation equal to 0 if you want to find when something hits the ground. So, two ways to find the equation. You can either use Desmos or you can use the graphing regression on our regular old calculators. So I'm going to use Desmos first. I'm going to show you how to deal with that like I did on the other problem on the other video. You go and you make your table. So you go to add table into Desmos, and then you type in the values for your time, 0, 0.2, 0.4, 0.6, 0.8, and then 1.0. So very quick here, 1 second is the biggest amount of time there. And again, you can see that this comes straight from this little table here, my times. And then I'm going to type in my values for my y's, my height of the football. So you have 10. This is when it was released. Obviously, it'd be in 0 seconds. 11.76, 12.24, 11.44, 9.36. You can see it's heading back down through these. And 6.0. Again, that is my y values from my points that were given to me in the table. Now what I can do is I can go through here and I can look at the points and see it goes up, comes back down. Remember, that doesn't mean that the person threw the ball straight up into the air. Remember, 10 feet is not very high here, so the highest it gets up here is 12.24 in these points. It may not be the highest point of the parabola. We've actually got to find the equation. The reason that looks so steep is because it's very quick. We're talking about a quick amount of time while that's floating through the air. So you got to remember our x-axis is time, not distance. So that's why it looks very, very steep here. So what we go to do next is we go to the next row and we tell the calculator, we tell Desmos to take the y values from list 1, and we're going to find the best fitting line using our little squiggly. Then we're going to do ax1, and then we're going to make sure that we have ax1 squared right there, plus bx, make sure we hit the little 1, plus c. And so then my graph will tell me what my a is, what my b is, what my c is. So you can see here that this one works out really nice because the textbook gave us a really nice problem to work with here. But this is my equation, and my a and my b and my c are given to me on the screen. So all I have to do now is take negative 16 as my a value. So that's negative 16x squared. 12 is my b value, and 10 is my c value. Those right there are my a, b, and c from the problem. And then what I could do to find out when it hits the ground is set this equal to 0 and see if I can solve this. Now we're going to come back to that here in just a minute. Before I do that, I want to show you on the calculator also how to do this regression again. So I go to Stat, I go to Edit, and I enter in my points, very similar to what I did when I was dealing with the actual values in the Desmos calculator. I'm going to hit 0 and then enter, and then 0.2 and enter, 0.4, enter, 0.6 and enter, 0.8, enter, and 1.0 and enter. Now I did that pretty quick with the keyboard. It takes a little bit longer when you're clicking the buttons, but it's still fairly fast. You guys can handle using a calculator. Then we plug in 10 for my first y value, 11.76, 12.24. Let's see if I can get that to work. There we go. 11.44, 9, 0.36, and 6.0. Again, you go to Stat and Edit to plug in the points, just like you go to the little table on Desmos. Then we're going to go to Stat Plot. So we're going to go to Stat Plot, second, y equals. We're going to tell the calculator to plot what I just put into stat. Yes, I'm being over-exaggerating here when I'm dealing with my words to try to help you out. You got plot 1 is turned on already. If it is not, you click enter and make sure on is highlighted so it will plot those points. Then I go to zoom and I go to zoom stat. I plug the points into stat. I go to zoom in on them with zoom stat. There we go. So there's my parabola. Notice on the calculator, it kind of zooms it out a little bit so it looks more what it might actually physically look like. But remember, the x-axis is still time, not distance. So then we want to find the equation. So we go back to stat, go over to calc or calculate, and go down to number 5, which is quad reg or quadratic regression. And it will find the best fitting line. Once I hit this calculate button at the bottom of the screen, it finds negative 16 x squared, 12x, 10. Same thing that I found with Desmos. Now, the final thing I want to do is kind of tie it back to solving as well. Because if we want to figure out when it reaches the ground, what we do is we solve this for x by plugging in 0 for y, because that would be the height at the ground. So when you solve this, you could use either the quadratic formula or you could try and see if this one factors. I honestly haven't checked to see if it factors, so we'll do it real quick and see. I can divide everything by negative 2. That would make this 8x squared, negative 6x, and plus 5. And when I look at that, it looks like it might factor. Let's check it out. Let's see. We could take this and do 2x and 4x would give me 8x squared. And then I've got 5 and I've got 1. So if I put, notice here, again, sorry, this should be a negative 5 over here. Mr. Harrison goofing up here. Should be a negative 5. You're going to have a plus and a minus. I'm going to put my negative here and my plus here. And then the factors of 5, I'm going to use 5 and 1. And if you do that, you'll have negative 10 and positive 4, which is negative 6. So it does actually factor. And so then what I could do is I could take this, set this equal to 0, set this equal to 0. And right here, again, because it's all equal to 0, that's why I can do that. Solve this, negative 1 divided by 2, so that's negative 1/2. Solve this, 5 over 4, 5/4, or approximately, well, actually we don't have to round that one because that one's pretty, 1.25 seconds is when it should hit the ground. This right here is negative. You can't have negative time. And the reason that that's the case, if you look over here at our graph, I'll zoom out just a bit, negative 1.2 right here is, or negative 1/2, excuse me, and then 1.25 there is where it hits the ground because it's thrown from 10 feet in the air, remember, and then it comes down and lands. This is actually not part of the real life solutions here because it doesn't go into the negative time. And so that's why it hits the ground there. But you could have also taken and done good old x equals negative b plus or minus square root of b squared minus 4ac all over 2a. And use that equation, that formula, to plug in your b, 12, your a, negative 16, your c, 10, and done all the simplifying here, and you still end up with 1.25 by the time you get to the end. So this will be negative 16 for A, and then over here 10 for C, all divided by 2 times negative 16. Simplify this, and you'd still get the same 2 answers at the bottom. And it should be a pretty nice little square root here because it does simplify down to factors, things that are factorable. You know that's going to happen right here in this. But you could do the same thing find out when it equals 0.